Hi, welcome to our next video about the span of a set of vectors, which we just saw that video, the 3 blue, 1 brown, chapter 2, which was all about the span and had lots of nice animations, so you could hopefully understand what it means visually. This video is going to focus a little bit more on making sure you understand the language about it and go into some other important facts about the span. So let's see. So it's the set of all linear combinations of the set of vectors. So you can write it in symbols using this, just with span, the word span, and then curly braces around the set of vectors. And it is, in set builder notation, the set of all results of doing linear combinations with those vectors, where the scalars, x1, x2, all the way through xp, they can be any real numbers. So let's go over this example to check your understanding of it, to make sure you understand some of this notation. So let's pause it here, and the answers will show up in about 10 seconds. Here's my answers. In the set uv, that just has two vectors. It has the vector u and the vector v. So just that point and that point. And that's only two vectors. But when we talk about the span of u and v, that represents any linear combination of them, which includes, like 1 times u plus 0v, which is just that point. It also includes 1 times v plus 0u, which is that point. It also includes 0u plus 0v. It also includes things like 2 times u, which is over here, or negative 1 times u, which is over here. And you get the idea. You get the whole line through those 2 points. And so there's an infinite number of points on that line. Now, are there any vectors that are in the span of u and v, but not in the span of u? The answer to this question is no. So the span of u and v is this green line I have highlighted here. But if you just look at the span of u, u is just this point there, but if you just look at the span of u, that's actually going to include v. So they're actually both equal to the same line. So you could actually say with an equal sign that these two sets are equal, like so. Now when we say two sets of objects are equal, both of these two things on either sides of the equal sign is really a collection of an infinite number of points. So it's different than just saying two numbers are equal or just two vectors are equal. We're actually going to do some writing of proof saying that two sets are equal like this later on. But right now I just want to give you a little sneak preview of how you might want to think about comparing sets. These are Venn diagrams, or as I like to call them, Ben diagrams. Anyways, what we're talking about is a situation like this, where if we draw the span of u, which I could actually just draw as all linear combinations of that vector there would just be this line. We're saying that that set of points is the same set of points as the span of u and v, meaning that anything that's in the span of u is also in the span of v, and likewise anything in the span of u and v is also in the span of u. So you got a situation looking like this. Like this. Okay, but this is a situation where the sets would overlap. There would be some points that are in one that aren't in the other one, some points in both, some points that are over there, but they're not equal at all. In this case, we say that the green set in the middle is a subset of the orange set. So everything in the green set would be a subset of the would be also in the orange set, but not vice versa. Here's the vice versa situation where there might be some things in the green set that are not in the orange set. But these are not the situation we're talking about here, so that's not what's going on here. Now, you can also see this if you want to describe this fact with symbols, that everything that is in the span of u and v is also in the span of u. What we could do is say, well, let's take a typical element in the span of u and v. That means it's going to be some linear combination of u and v. Like so. So if b is a vector in the span of u and v, what we're saying here, that means it's a linear combination of u and v. And then there's a trick we can use. Here's my little proof written out here. And the trick is that, the vector v is equal to 3u. So in this expression here, we can just replace the v here with 3u, because if you do 3 times 1, you get 3, 3 times 2 is 6, and you can also see they're in the same line. So then when you rewrite b as this linear combination of x and v, but writing it in terms of u, you can then just use the distributive rule, which does work with vectors here, by the way. So you can rewrite this as x1 plus 3x2 times u, and that is a linear combination of u, which means that this vector b is in the span of u as well. Okay, here is another conceptual exercise for you to do. Given these two vectors, v1 and vw, and then these two other vectors, b and c, answer is each of these 6 statements about the set of vectors true or false. So this is an important thing to practice, is understanding the language and how linear combinations are related to statements about the span and solutions of linear systems and everything. So let's pause it here and check our answers after the pause break. Here's what I got. For the statements that are talking about vector b, all of these are false. So the linear system that we're talking about here with this augmented matrix is what I drew right here. It's a little bit small, but you see what I mean. 3x1 plus 8x2 equals 2, and so on. And if you reduce this matrix to reduced echelon form here, you see that the last row corresponds with the equation 0x1 plus 0x2 equals 1, which means that that's impossible. There's no way to make this true, so it has no solution. So that means the system is not consistent, because consistent means it has a solution. Okay, so now what about this vector equation here? Does that have a solution? Well, I went ahead and wrote out this vector equation, x1 times v1. I'm just replacing v1 with 3, 2, 3 here. So doing x1 times that vector just multiplies each of the entries by x1, and then do 818 times x2 multiplies each of those entries by x2, and we want to know, is it possible to scale these in such a way that the result ends up being 213? So in other words, the result of adding these together is just the result of adding up each of the entries here. And looking at this, you can see that saying that two vectors are equal is the same thing as saying that each of the 3 components of the 3 vectors are equal, which is the same thing as a system of equations. So again, this system of equations here is the same thing, really, as this vector equation. This is really just 2 different ways of saying the same fact about x1 and x2 and its relationship with these vectors. Okay, so yeah, all of these are false. Saying b is in the span of v2 is the same thing as saying that b is some linear combination of v1 and v2, that there's some way to write b as this result. And so if this equation doesn't have a solution for x1 and x2, then b is not a linear combination of v1 and v2. So this statement is false. Now, with the second one here, yeah, you might have figured out that these three different things are really three different ways of saying the same thing. The linear equation is, sorry, the linear system is consistent. The vector equation is really the same thing as this linear system with the augmented matrix. And when you row reduce the augmented matrix, sure enough, you get a solution. So it is consistent because that's your solution. That's the same solution for x1 and x2 here. And because it's possible to write C as a linear combination of V1 and V2, it means that C is in the span of V1 and V2. Okay, so this exercise was basically a way for you to convince yourselves that this important fact is true. What this says is, given any vectors, so p different vectors labeled v with different subscripts, and then another vector b, and the b is going to represent the one on the other side of the equal sign in these equations. So what this is saying is that these three things are all equivalent statements. So for any particular set of these given vectors, these are either all true or they're all false. And we saw an example of this in the last one. These three statements are basically the same as the three statements we had two copies of with that true or false question. So we can say B is in the span of V1 through VP. That means B is a linear combination of V1 through VP, meaning we could write that fact as a vector equation. It is possible to write B as a linear combination of the V1 through VP vectors. And that's the same thing and this vector equation, remember, we could actually write out the left side as a vector and the right side as a vector, and you end up getting the same system of equations that is represented by this augmented matrix. And by the way, how do we tell that this system is consistent usually? Well, we row reduce this matrix and then look for the pivot positions. And if there's a pivot in the last column, in the B column, that means there's a row of the form 0, 0, 0 equals 1, which is automatically false. And so this has no, the system has no solution, and also the vector equation has no solution, and the rest of these are also false if it does have a pivot in the last column. If it does not have a pivot in the last column, then all of these are going to be true for that combination of vectors. All right, so this is an important concept, the span, the language about the span and sets of vectors, and what it has to do with linear systems. So if you're struggling with this, if you're struggling with the geometry of it, definitely watch the 3 blue, 1 brown video, chapter 2 about the span again. Otherwise, if you have other questions about the language, maybe ask those in class or in office hours. And I'll see you later.